first talk this afternoon is by Rodolfo Aguilar from University of Miami on homology planes and fundamental group.
Yeah, that's it. Thank you. Well, thanks for the introduction, and let me give you the plan of the talk. So I will divide this talk in 3 parts. So I will begin by motivating all the talk that I'm going to give, and I will call this part around Ramanujan Surface. So I will give an example of an algebraic surface, and I will give some properties of it. And then in 2, I will talk a little bit about homology planes. And then I will finish by giving some ideas of an algorithm to compute the fundamental group, or a presentation of the fundamental group of some homology planes. So let me see if we can read all of this. Okay, so let me begin. We will be interested in something as follows. So we will consider X, Y, and Z smooth affine surfaces. And the example that I'm going to present comes from what it's called a cancellation property. So we say that this triple satisfy the cancellation property if when we have an isomorphism between the product of X times Z to Y times Z, this is an iso, then this isomorphism induces an isomorphism between X and Y. Okay, so when we have 3, let's say, smooth affine surfaces, everything will be over the complex numbers, and we have an isomorphism of this product, we can cancel this Z. We say that this triple satisfy this cancellation property. So let me make a remark here. So historically, we are in the 70s, and in the paper of Ramanujan, he said that it was believed around the 70s that any smooth contractible, and I will put it in parentheses, affine and rational surface is isomorphic as an algebraic variety to C2. So Ramanujan was working on this, was thinking in this cancellation problem, and then he found a counterexample to this. And not only that, he found a characterization, a topological characterization of C2. So let me begin first with this. So it was C.P. Ramanujan. Around 71, who showed the following. So let X be a smooth, contractible surface we need to add an hypothesis which is simply connected at infinity. So I'm going to define what this means. And then he showed that this X is isomorphic to C2 as an algebraic variety. So we have seen in talks of Claire-Voisin the topological characterization of some fourfold, and now we have a topological characterization of this of C2 as an algebraic variety. Okay, so let me define what does it mean to be simply connected at infinity. And for this, we suppose that we can write X as X bar minus D, with X bar a smooth projective surface, and D a simple normal crossing divisor. So we will take a regular neighborhood of this D closed inside this compactification X bar, and we call the fundamental group P1 of the boundary of this tubular neighborhood, closed tubular. We call this fundamental group the fundamental group at infinity of the variety X. Okay, so we can define this fundamental group at infinity in several ways. So I will choose this one. We choose a compactification that is S and C, and then we take a regular tubular closed neighborhood. Then we take the boundary of this, and this is going to be called the fundamental group at infinity. So if this is trivial, then we get that it is simply connected at infinity. Okay? And now let me I don't get it. So where are you?
So what is the fundamental group at infinity of?
Ah, that's trivial.
What is D?
The,
Of P1, right?
yeah.
What is D
For C2 we have no P1, right? Because we need to take, for example, for C2, for C.
Yeah.
That is P2 minus.
Yes, P2 minus a line, right?
Minus
Yeah.
P1.
Yeah.
Yeah, so we take a tubular neighborhood of this, and we are getting a sphere, if I'm not mistaken. So we get a sphere, and the fundamental group of this sphere is trivial.
It is 3.
Yeah. So that's right. No, it's not. I mean, to prove this, you will. We need to use a theorem of Mumford that says how to compute this fundamental group at infinity. You have a presentation that depends on some graph that is the dual graph of this divisor at infinity, and then Mumford gives you an algorithm to, when you have a tree, you can compute this, and you see that when you have different ways of compactifying, this fundamental group is not changing. Okay, any other question? So now, I started with some cancellation problem. Let me give the example that Ramanujan showed. So let's consider C1 and C2 be plane curves with C1 a smooth conic and C2 is being a cuspidal cubic intersecting in the following way. So they should intersect, C1 intersects C2 transversally at some point P plus 5 times at some point Q. So now let me make a design of this. So we have a cuspidal cubic. It is transverse at some point P here. So this is C2. This is C1. And we have a point intersecting with 5 times here. Okay? And now we need to consider the blow up at P of P2 and we need to write C1 prime and C2 prime, the strict transform of these two curves, C1 and C2 respectively, okay? And we will define X as this blow up at P minus this strict transform C1 union C2. So this is the Ramanujan surface that I'm going to be talking about in this first part of the talk. So essentially what we have done is we blow up this point P, and now this is going to intersect only here, Q, this is C2 prime, and this is C1 prime. We remove this from the blow up of P2, and Ramanujan showed that X is contractible and, well, smooth. So it gave a counterexample to this by showing, he showed the following, but the P1 of this divisor, sorry, the P1 of this manifold here, three-manifold, is not trivial. So actually this is more. This is even only if, then it is also valid in this way. So it's really a characterization. We can show it in other way. So we can say that the logarithmic codida dimension of this surface is actually 2. So it is of log general type. It cannot be isomorphic to C2. Okay? So now he asked the following question. Is X times C isomorphic to C3 as algebraic varieties? So And now we enter with some theorems on cancellation properties. So let me make a theorem of Itaka and Fujita. This was around 76. That says the following. Let X and Y be smooth affine surfaces. Then, if the logarithmic coded dimension of Y is bigger than 0, and we have an isomorphism of X times Cn Y times Cn, then the cancellation property holds. For X, Y, and Cn. So what this is telling you is that we have this isomorphism, and then we can cancel out this Cn, right? This is going to be isomorphic. So the corollary of this is that Cn admits exotic algebraic structures. And so the idea of the proof is that you can use the H-covordism theorem for n bigger than 3. So you consider something like this, you multiply by Cn, and then by the H-covordism theorem you get that they are isomorphic as real varieties, and then if they were isomorphic as algebraic varieties, you use this Fujita theorem and you could cancel, finding that this X is going to be isomorphic to C2, but that contradicts the Ramanujan's theorem, so they are actually not isomorphic as algebraic varieties. Okay? Is this clear? Any question?
In the case of exotic differential structure, there is classical Munar Gerber interpretation in terms of homotopy groups. Here, is there something like that?
I don't know. I know nothing about that. Sorry. Yes. Let me. I will give more exotic structure, but not in that terms. So this gives some algebraic exotic structure, but actually we have much more. But I don't know about that. So we have also some analytic exotic structures. So we can continue with this Ramanujan surface or this idea, and this is due to Seidenberg around 93, and it says the following: it is an analytic cancellation problem. So this is an algebraic cancellation problem, but if we have X and Y affine smooth surfaces with maximal logarithmic collider dimension. So these surfaces are of low general type. Then we get again that the cancellation property holds for X, Y, and Cn. And so again we get a corollary of this, is that Cn admits, and actually he found a countable set of analytic exotic structures.
We know it's countable. No period of that.
We don't know. I don't know. Yeah, he just constructed a countable number of surfaces that I will be calling homology planes in what follows of contractible and that are pairwise and non-isomorphic. So we don't know.
I kind of missed the corollary.
Here? Yeah, so the sketch of the proof is that using the H-coverdism theorem, we can find that X times Cn is isomorphic to R2n plus 4 as real manifolds, okay? And then, using Ithaca cancellations, we can show that this product is not isomorphic to Cn plus 2 as algebraic varieties. Why? Because if this were the case, we could simply cancel the Cn by using this cancellation theorem, and then we would get that X is isomorphic to C2. And then this will contradict the Ramanujan theorem, the Ramanujan example. Okay?
So this X is that.
Yeah. Yeah, I should have said. Oh, yeah.
And that under is kind of like written, so there's no moduli or vary those. Otherwise,
yeah, you're right. I don't know. Yeah, the answer is that I don't know. Yeah, sorry.
By the way, the answer to that question.
Yeah, thank you. Yeah, so the answer to this question is no.
So how does this theorem, what is it in this theorem that
the cancel?
Is not weaker than that?
Yeah, I forget this.
Analytic.
Yeah, so this is going to the analytic category, and this is to the algebraic. So this is giving an algebraic exotic structure on Cn, and this is giving an analytic exotic structures. Okay?
Presumably more of this.
Sure. But it doesn't stop there. So I don't know which time is it. Yeah, the argument is the same. We just need to know this. So we have, let me call this beyond analytic. So actually using this same surface, so let X be the Ramanujan surface. So this is work of Seidel and Smith around 2005. They show that x to the power m, this is isomorphic to r to the power 4 M, and that it induces a symplectic exotic structure on R to the 4M, which is convex at infinity. So I'm not going into details here. It's not really necessary. But we can still get in results of these Ramanujan surface, and then let me give a final remark. So by the way, the proof of this is much more complicated. You need to compute some symplectic homology. Yeah, I think that's the case. But M equal 1. I'm missing something. Yeah. So, yeah, thank you. So M equal 1 in 1.
No, so because X is a surface, right? So it's dimension 4 as a real.
Yeah.
But I was still thinking if you did it for M equal 1, that equals like the product. Maybe I'm wrong.
But I mean, the problem that with M equal 1, we have this fundamental group at infinity, yet that is not going to disappear. It disappears when we go to higher products. So probably is, yeah. Yeah, my bad.
Well, it'd still be enough to do it,
But that would be hard.
Yeah. That will be more difficult. Okay, so let me close this section with the following thing. So recently, SAP used a generalization of the dual graph of the divisor at infinity of the Ramanujan surface to construct new plumbed homology spheres bounding contractible manifolds. So this is a topic that is apparently well, the people from 3 manifold are interested in. So they search plumbed homology spheres that are bound in some contractible manifolds. Well, we can ask a question here that if this R to the 4M admits a countable number of exotic symplectic structures, just like in the Seidenberg theorem, but I think we don't know that yet. Okay, so before I continue, any other question? So let me go now to homology planes. So that finishes this long introduction with the Ramanujan surface. And now let me go to homology planes. So the definition is as follows. So we take let X be a smooth surface. Now, if the integer homology vanishes for I bigger than 0, then we call X a homology plane. Now we can replace this set by Q, and we can say that we have a Q homology plane. Okay. And now, well, the example that we have been treating is the Ramanujan surface. Is a homology plane. So using the construction as a pair, as a projective variety and a divisor, we can get some criteria of when a pair gives you a homology plane that it's similar to the talk of Andras. So you will need to have a plumbed graph such that the corresponding divisors are rational curves, that the plumbed graph is a tree, and you will have some conditions on the homology, on the two homology, but let me skip this. So now, I was saying that I put rational in parentheses in the very beginning because we have a theorem of Shastri and Gurjar around 87, if I'm not mistaken, that says the following, that says homology planes are rational. And the proof of this goes by using the classification of projective surfaces. So it's 2 papers, quite long, just using this classification of surfaces. Okay, so let me see that I'm not forgetting.
So it's X affine.
Sorry, this implies that it's affine. This is going to imply that it's affine. Yeah, but I mean we can put it if you want, but this condition is sufficient, so imply that it's going to be affine. Okay, and now I'm going to be interested in fundamental groups. So I was working in something like trying to find complicated fundamental groups in quasi-projective surfaces by the so-called Shafarevich conjecture. And so we were searching groups, infinite groups, that such that the abelianization is finite. So we will lead to this kind of surfaces, and they are more or less classified. So let me tell you a little bit about the classification. But for this, let me tell you a theorem of Tom-Dick and Petri. Don't remember the year of this. So let X be a homology plane. So now so it admits X bar and D as before. So we have that X bar is a projective surface and D is a divisor on D, such that we can write X as X bar minus D, and we have a morphism phi from X bar to P2. So what this is telling us is that we can get the homology planes out of P2. And let me write a definition. If the image of this divisor D is an arrangement of line, let me call it A, then we say that X admits a linear plane divisor. So it was believed at that time that every homology plane could be obtained in this way. After some time, some counterexamples were shown. Yeah, it is supposed that it comes from an arrangement of five lines. So you should make some Cremona transformation, some logs, but Tom, Dick, and Petri claims that it's possible. I don't actually know the way exactly, but
they kind of prove it.
yeah, I mean it's not a constructive something like an algorithm. Okay, so let me give you the classification of these homology planes, and this is a work of a lot of people, so I will just mention some of them. So this is Fujita, 79, Gurjar, and Miyanishi, 88, and Tom, Dick, and Petri, and some people more. So let X be a homology plane. And we are going to do the classification but by logarithmic codata dimension. So if the logarithmic codata dimension of X equals minus infinity, then X is isomorphic to C2. So we don't have more in this case, and this is the case also for codata dimension equal to 0. The codata dimension?
Or even just the number of
the codata dimension is defined. So suppose that we can write X as X bar minus D.
Yeah.
And then the logarithmic codata dimension of this X is the supremum of the dimension of the pluricanonical map plus D. So we have a linear system here given by Kx plus D of X bar.
But you would know if you knew the degrees of the complement, you could figure out the arguments just from those.
I don't.
MKX, well, maybe not. Sorry.
Yeah, you need to put an M here.
Like numerically, if you can figure it out numerically just from knowing the degrees of the components.
I think you can know it, but it's quite complicated because the dual graph can be complicated.
But then
But there are some numerical conditions. Yeah.
then you'd have to know the dual graph if you can't figure it out.
Yeah. That's so there are no homology planes with Kx equal to 0. And now, if we have logarithmic codata dimension equal to 1, then all homology planes arise from something called a quasi-pencil. So this quasi-pencil is something like this. So you have an arrangement of lines that has only one higher multiple point, and you have a transverse line, and this is called, let me write it like this, L1N. So you have N lines here plus 1 transverse. And they all arise from this when you have codata dimension equal to 1 by blowing up this point and then using an algorithm. You need to make a tree out of the dual graph of this and to compute some some numerical invariance. And for so this was proved actually before the Seidenberg example. So it says that there exists an infinite, well, a countable, I would say, countable number of homology planes with a logarithmic codata dimension 2, that is of general type, coming from an arrangement of line. So with this, I want to say that they admit a linear plane divisor, and actually Tom, Dick, and Petri, they gave an algorithm to compute a countable number of homology planes when you already have an arrangement of lines. So this is the first in the classification, and well, let me put it like a theorem. So Tom, Dick, and Petri. There are only a finite number of arrangements of lines being a plane divisor for homology planes. With codata dimension, logarithmic codata dimension equal to 2. So of course, when we have logarithmic codata dimension 1, for every n you will have here a different arrangement. But when you are in the general case, in the logarithmic codata dimension type equal to 2, then there exists only a finite number of them. So for example, let me give you L2. L2 is an arrangement of 4 lines in general position. Let me give you L3. L3 is this arrangement plus 1 line passing by through double points. And Tom, Dick, and Petri says that we can obtain the Ramanujan surface out of this arrangement of lines. So, okay. There are a finite number of arrangement of lines, but when you get something like this, you have a dual graph, right? And then you will blow up, because this is not a homology plane, the complement is not. You need to make some modifications. You need to make some blow-ups, and the choice for these blow-ups could be countable. So I mean, if you start with only one arrangement of line, you can get a countable number of homology planes. But what I want to say here is that the image of this compactification that I wrote is going to be used only one of these, of some finite number of, and actually there are only 7 families counting this, and at most 13 lines. Okay. Okay, so actually we have a lot of questions when we have an arrangement of lines, a homology plane coming from an arrangement of lines. So what can be the fundamental group if it's not always contractible? We can ask about the the boundary manifold of these homology planes and which groups can appear as this, but I'm going to go to the third part. So I'm going to present the following theorem. So there were no general method to compute the fundamental group of these homology planes. So we were actually interested in some concrete examples. And so we had to develop an algorithm. So there exists an algorithm to compute a presentation of the fundamental group of a homology plane admitting a linear plane divisor. So let me give you how is the construction of this algorithm. So we have some steps. So in the first step, we need to compute a presentation G and with generator x1 until xn and some relations. For the complement for the fundamental group of the complement T2 minus A with A, this plane divisor. So there are several ways that we can do this. So we can compute it with braid monodromy. We can compute it with Van Kampen, or we can use the boundary manifold, the Euler neighborhood of the divisor at infinity. And then when we have this, we need to blow up the points P of multiplicity bigger or equal to 3, the points of A of multiplicity and now this was already known, so this is some classical work. The difficult part comes in the third part that says we need to find a word WP in these generators representing a meridian around these exceptional divisors that I will denote by EP. And now, once that we have normal crossing and that we have a word for this, we just need to add some relations to this presentation. So we need to add some relations of the form WP to some power times some X Y to some power. So the presentation G.
With the X is not just the hyperplane.
No, Yeah, so for example, in the case of the Ramanujan surface,
Yeah.
this is the blow up of P2 at some point, right?
Yeah.
Minus the strict transform of C1 prime union C2 prime. So we are actually forgetting the exceptional divisor. We are not removing. If we remove the exceptional divisor, so this is isomorphic to the complement in P2 of this.
Of the hyperplane arrangement.
Yeah, of these two.
Well, not if there is not a hyperplane.
So there is some partial compactification, we can call it. So actually this algorithm works more general, for more general surfaces, not only for homology planes, for some partial compactifications, and it can be used in more.
So the point when the hyperplane arrangement is you're blowing up the points multiple bigger and then takes a strict transform.
Yeah.
But you're throwing out these, and that's why you can.
Yeah, because we can get something like this. So we blow up, and we get an EP here. We need some meridian around this because we can be removing the strict transform of the lines, but not this.
Yeah.
So we need an expression for this.
Yeah.
So this is the whole thing of the algorithm is to find this, and you can read it for some presentation out of this. So I don't think I'm having time to do this. So just let me give you some consequences of this. So some applications. I didn't write it, but we have a theorem of Orekov that says that when you have a homology plane, you cannot have a ciphered homology sphere bounding this homology plane. And so an application of this is that if we compute the presentation for L1n, we can obtain fundamental groups of homology planes isomorphic to fundamental groups of ciphered homology spheres. So they cannot bound a homology plane, but the fundamental group of a ciphered homology sphere can be the fundamental group of a homology plane. As a second application, we get new structures, new exotic structures. Let's say algebraic or analytic in C2, Cn, then. And actually what I was really interested in the thesis is that we get homology planes of log general type. So the logarithmic data dimension is 2 with infinite fundamental group. And actually the way of proving that this fundamental group is infinite is that it admits a quotient, an infinite quotient that is isomorphic to the fundamental group of an orbit curve. So as the people were interested in contractible homology planes, they didn't really search for the fundamental group of the other homology planes. So as long as I know these are new examples, they were known. And to 2 questions. So the question that it's really important to algebraic geometry or the topology of algebraic geometry is if there exists a fundamental group of a smooth algebraic variety, an infinite fundamental group that doesn't admit any linear representation, an infinite linear representation. So this was the motivation also of this. But as we found this kind, it admits a linear representation. So the question will be, if X is a homology plane with infinite fundamental group, does it admit a linear representation with infinite image? And a second would be, can we use the tools of 3-dimensional varieties, 3 manifolds, let's say, to study homology planes? So we can study, well, we can try to study homology planes with these kind of tools, or we can try to study the first questions by using something like this. And because the topology of algebraic varieties is usually studied by Hodge theory, and now here that we don't have any information, it basically gives you nothing. So the arrangement of line is studied, for example, by characteristic varieties, but we don't have homology, so we really need to get more tools from other places here. Okay, so I think I'm stopped here.
I'd like to thank the speaker for a very nice talk. And are there further questions?
Actually, I had a question. You said you can't use Hodge theory.
A little louder.
When you said like you can't use Hodge theory, I mean, you can certainly do like all kinds of things like running manifolds, right? I mean, you might not.
Well, I mean, we cannot use like the classical stuff of Hodge theory. Maybe we can use like representations to higher dimensional groups like SL2, or I'm not sure. But I mean, the basic stuff is not.
There's no homology.
Mm. Yeah. Yeah, so we cannot consider an infinite the abelian universal abelian cover in studying variants over there. Yeah, we can't. Cannot.
So
Yeah.
are there any finite Cal covers? Like is the in a homology plane can it have any finite Cal covers, or is that?
I don't know. I mean, of course, but I don't know if it's going to be a tal.
Finite index normal subgroups in the
Yeah, that can happen.
okay.
Yeah.
I guess what I was more saying is like if you look at like the spectrum of Laplacian or something like that. I mean, it doesn't have to.
Okay. Yeah.
I understand there's no homology. But that
Yeah.
doesn't mean that, like,
Sure. Maybe I was too.
you can't get something else like Laplacian.
Yeah, you need more sophisticated methods. Yeah, but I don't know. I haven't tried. I haven't looked any of that. Thank you.
Cover? Is it still another homology?
It's difficult to compute that in general, right? Yeah, I don't know.
Could I ask a question? Can you hear me?
Yeah. Wait.
Thanks. So that was very interesting. I have a question about you mentioned that you have some homology planes who has a fundamental group that's the same as an orbit curve.
you upload.
Fundamentally the same as an orbit curve for some homology planes.
So when we have the orbifold fundamental group of what? Of a surface?
You said there was a case where you have a fundamental group of a homology plane that's also the fundamental group of an orbit curve.
That admits a quotient, an infinite quotient to an orbit curve.
But,
so yeah.
Yeah. Does that have a map of algebraic varieties to the orbit curve also, or not? Or
Sure,
do you
sure.
not know?
Yeah. I mean, like you kind of use the Arapura theorem here, and you can find an explicit, a map to the orbit curve, and then we get that this is actually induced by some geometric map that actually comes from the arrangement of lines.
Okay. So that means that map has some multiple fibers or something like that.
Yeah, sure.
Okay.
Yeah.
Okay, thank you.
Okay.
So, no other questions? I'd like to once again thank the speaker, and next talk is